My name is Liao Junhua. The paper I'm presenting today is titled "The Lightweight Model for Active Speaker Detection." Active speaker detection is a challenging task to detect who is speaking in one or more speaker scenarios. Existing studies have attempted to improve the performance by inputting multiple candidate information and design complex models. Although these methods have achieved excellent performance, their high memory and computational power consumption render their application to resource-limited scenarios difficult. Therefore, this study proposed a lightweight active speaker detection method. Experimental results on the AVA active speaker dataset reveal that the proposed framework achieves competitive maps performance while the resource costs are significantly lower than the state-of-the-art method, particularly in model parameters and flops. In summary, the contributions of this paper are as follows. 1. A lightweight design is developed from the three aspects of information input, feature extraction, and cross-model modeling. Subsequently, a lightweight and effective end-to-end active speaker detection framework is proposed. In addition, a no loss function is designed for training. 2. Experiments on AVA active speaker or benchmark datasets for active speaker detection released by Google reveal that the proposed method is comparable to the state-of-the-art method, while still reducing model parameters by 95.6% and flops by 76.9%. 3. Ablation studies, cross-dataset testing, and qualitative analysis demonstrates the state-of-the-art performance and good robustness of the proposed method. Several active speaker detection methods use 3D convolutional neural networks as visual feature encoders. Although 3D convolution can effectively extract the spatial temporal information of phase sequences, it requires numerous model parameters, and its computational cost is excessively high. To construct a lightweight visual feature encoder herein, the 3D convolution is split into 2D and 1D convolution to extract the spatial and temporal information from the candidate phase sequences respectively. Compared with 3D convolution, this method can significantly reduce the number of model parameters and the computational burden while maintaining good performance. Currently, male-frequency substrate coefficients (MFCC) is among the most widely used methods in audio recognition with the aim of improving the accuracy of speech activity detection. Therefore, similar to most existing active speaker detection methods, herein a 2D feature map composed of 13D MFCC and temporal information is extracted from the original audio signal as the input of the audio feature encoder. However, the general concept of the aforementioned studies that use the 2D convolutional neural networks to extract audio features is not followed herein. Instead, the idea of lightweight visual blocks is adopted and the 2D convolution is split into two 1D convolutions to extract information from the MFCC and temporal dimensions respectively. The multimodal features FAV obtained by summarizing the visual feature FV and audio feature FA are inputted into the speaker detector. The architecture of the detector is shown in Figure 5. First, the bidirectional GRU models the temporal context information of multimodal feature FAV. Next, a fully connected layer predicts whether the candidate is speaking. The proposed active speaker detection loss function is composed of only the mean classifier and the visual auxiliary classifier. We introduce the temperature coefficients into the binary cause entropy loss. The introduction of temperature coefficients allows the model to avoid falling into a local optimal, provides more opportunity for exploration in the early stage of training, and helps the model pay more attention to difficult steps in the later stage of training to further improve its accuracy. The performance of the proposed framework is compared with that of other active speaker detection methods on the AVA active speaker validation side, and the results are summarized in Table 1. The MAP of the proposed method reached 94.1%, which is only slightly inferior to the 94.2% of the state-of-the-art method scale, with 23 times fewer model parameters and 4 times fewer computations. In addition to evaluate the robustness of the proposed method, it is further tested on the Columbia dataset. Without fine-tuning, the proposed method achieves a state-of-the-art average F1 scores of 81.1% on the Columbia dataset compared with TalkNet and LocalNet, showing good robustness. In addition, we have demonstrated the robustness and effectiveness of our methods through a large number of ablation studies. On the benchmark AVA active speaker, we break down the performance of the proposed method according to the number and size of phases. First, the validation set is divided into three parts according to the width of the detected phases. Although the performance of all the methods decreases with a decrease in phase size, the advantage of the proposed method is more significant. Second, the data are divided into three mutually exclusive groups based on the number of phases detected in a frame, which account for approximately 90% of the entire validation set. The performance of all methods decreases as the number of phases increases. Although the proposed method only inputs one candidate per step to reduce computational complexity, it consistently outperforms state-of-the-art methods with multiple inputs for different number of detected phases. You can obtain our code and model widths from the project page. That's all. Thank you.